Hi everyone! In this lecture, I will show you what a reduced row echelon form is and how can we use this form of matrix in order to solve a given system of linear equations via a method called Gauss-Jordan method. So, let's start with the very simple definition of what is a reduced row echelon form is and then continue with the Gauss-Jordan method. Okay, here's the definition. As we all remember from the previous lectures, we know what a row echelon form is. So for a matrix to be in reduced row echelon form, and we can also simply write it like this, RREF, we can use an abbreviation, right? And REF just reduced row echelon form, and RREF is just reduced row echelon form. Okay, so it needs to be first in row echelon form. And what is that? Which means, if you have a square system, as we all remember, we draw the main diagonal, right? Just a quick reminder, if it's a square system, which means we have an equal number of rows and columns in the matrix, then we just draw the main diagonal and look at the entries below the main diagonal, right? If it's an upper triangular one, if all the entries below the main diagonal is are all equal to 0, then it's called a row echelon form. And if it's not a square matrix, then again we look at the number of zeros in the successive rows. In other words, if we have no 0 in the first row, then we must have at least 1 0 in the second row, right? Say this is the very first element in the first row, and this 0 is the very first element in the second row and in the third row. And then again we look at the second row and third row, and we must have at least one more 0 at the below row, right? If the second row has 1 0, and then third row must have at least 2 zeros, which is strictly greater than the one above it, right above it. And in this manner we just look at the leading number of zeros in each row. Okay, and if we have if the number of leading zeros for all rows, of course, at the k plus first row is strictly greater than the row right above it, then we're done. That means our matrix is in row echelon form. Okay, and this is what the row echelon form is. Okay, for a matrix to be in the reduced row echelon form, first of all it needs to be in row echelon form. And what makes it different are the following two additional properties. In addition to being in row echelon form, a reduced row echelon form must satisfy these following two properties. And the first one is that the leading entry in each non-zero row is 1. So what it means, the leading entry in each non-zero row. And a non-zero row, as we all remember, is a row there is at least one element which is not equal to 0. It is called a non-zero row, right? If all the elements in a row are equal to 0, then this is a 0 row, because the only value in that row is 0. But if there is at least one element which is not 0, then it's called a non-zero row. So in each non-zero row, the leading entry, and by this terminology, the leading entry, I mean that the very first element in that row which is not equal to 0. So the first element from left hand side to the right hand side. Of course, we read the rows by convention from left to right. So when we read the values in that row from left to right, the first element which is not 0 is called the leading entry in that row. So all the leading entries in each non-zero row should be equal to 1. And another property, the third one, is that each leading one is the only non-zero entry in its column. So after finding the leading ones in each row, we check out to see if all the entries in the same column besides the leading one are equal to 0. Okay, it means that there is much more work for us to understand whether a given matrix is in the reduced row echelon form or not. Okay, let's give a simple example to understand what I mean. Okay, here's the example. Suppose this is the matrix given us, right? This is the matrix. We suppose we are given a 3 by 4 matrix, and is it in the reduced row echelon form? Let's see. Okay, the question is that this matrix is in the RREF form. Okay, well, first of all, it needs to be in what? It needs to be in row echelon form, and since this is not a square matrix, I just check to see the number of leading zeros in each row, if it satisfies the row echelon form condition, right? So in the first row there is no leading zero, right? And in the second row we have one leading zero, and in the third row we have two leading zeros. And leading zeros means the number of zeros up to the value in the same row which is different than 0. So you see the first 0 in the second row, but then there comes the value 1, right? So we just count the number of zeros before we find the first non-zero element in that row. This is the way we call the leading zeros, right? So as we notice that the number of zeros strictly increases, right? The number of zeros from top to bottom strictly increase. In other words, in the first row I have no 0, in the second row I have 1 0, and in the third row I have 2 zeros, which means it is in the row echelon form. Okay, now let's look at whether or not the other two properties are held. So the leading entry in each non-zero row must be equal to 1, the leading entry. So okay, we go through all the rows and see whether or not the very first element, which is not 0 in each non-zero row, is 1 or not. Okay, for the first row, the very first element which is not equal to 0 is 1, and this is a non-zero row, right? Because there are values which are not equal to 0, so this is a non-zero row of the first row, and the leading entry is 1 for the first row, and it is satisfied. Okay, and the second row, you see, the leading entry in this non-zero, this is also a non-zero row because there are values different than 0. Okay, and the leading entry, the very first element which is not 0, is 1 again. So the leading entry is 1 in this row as well. How about the third row? And third row satisfies the property as well, right? The second condition is held for this row because after passing these zeros, after passing the last 0, right, you see the first element is 1 again. So the leading entries are all 1s, and second condition is satisfied. How about the third condition? This is the only condition left behind for us to see whether or not it is satisfied. Okay, each leading one is the only non-zero entry in its column. Let's see, is this true or not? Okay, for the first row, you know the leading entry is 1, and the column, let's use a different color to bring your attention on that point. Okay, the leading entry in the first row is 1, and I just circle its column, and we see that besides the value 1, all the other values are equal to 0. So the leading entry 1 in the first row is the only element which is non-zero in its column. And we do the same for the other leading entries. For instance, in the second row, the leading entry is 1, and I just circle its column where it is included, and you see besides the value 1 all the other entries both below and above it are equal to 0, so it is satisfied again. How about the third row? And the leading entry in the third row is 1 again, and if I look at its column again, I see that all the values besides the leading entry are equal to 0, which means that all the conditions are satisfied. And what it means is that this matrix is in reduced row echelon form. Okay, and this is what a row reduced row echelon form is, and this matrix satisfies all the three conditions. All right, why this property is important, or why this definition is important for us? It also, you will see that when we apply Gauss-Jordan method, it also helps us to decrease the computational cost caused by the back substitution method, and makes things simpler for us. But before that, let's first define what a Gauss-Jordan method is, because this is the technique that we will be using in this lecture to solve a system of linear equations. Okay, I do it in an algorithmic manner. So an algorithm is nothing but a set of rules that we should follow to produce an output where we are given an input. Okay, and our input in this problem is that given any arbitrary system of linear equations, okay, we are given an arbitrary n by n system. This is our input. And what is our output? Our output to this problem is the solution set that satisfies both equations in this given system simultaneously. We're trying to find them. And in the meanwhile, we define step by step the procedure that we should follow in order to produce this accurate result. Okay? And here is the algorithmic flow for us to produce the solution by using Gauss-Jordan method. And in step 1, we represent our system in the matrix form again. Right, this is something that we're familiar with based upon our previous lectures, you know, as we all learned from Gaussian elimination method, while we are applying the Gaussian elimination method, we first represent our system of equations in the matrix form, and the matrix form is that the augmented matrix, right? So each row actually corresponds to one equation in the system, and from top to bottom I just put the equations in the matrix form, right, in each row. And then in the second step I control, or I check to see if this form, if this matrix is in reduced row echelon form or not. If our answer is yes, then there is nothing to do for us, okay, because it is already in reduced row echelon form. Then we are ready to apply Gauss-Jordan method, nothing left for us to do. But if it is not in reduced row echelon form, and if our answer is no, so then what we are trying to do, and we will try to do, convert this augmented matrix form into that of equivalent reduced row echelon form. So again, we convert our matrix form into another matrix form known as reduced row echelon form, as just we defined above. And then when we reach to that point, when we have a reduced row echelon form, then we're done with Gauss-Jordan method, and we again apply back substitution method to find the solution to the given system of equations. Alright then, let's a quick reminder again before proceeding with the solution of a system using Gauss-Jordan method. And you know, if it is not in reduced row echelon form, then we need to convert it into that form. But how can we do that? As again, just like we did in Gaussian elimination method, we are allowed to perform elementary row operations. And what are these elementary row operations again? Just a quick reminder, as I said, just a quick note. We are allowed to perform 3 legal operations on this matrix form, and the first one is what? The first one is swapping 2 rows, right? We can swap 2 rows, namely say Ri and Rj represent any arbitrary rows in the matrix. We can swap them, so we can replace one of the rows with the other one, and this does not change the solution set at all. We all talked about that, right? These 3 conditions or these 3 operations allowed us to perform do not change the solution set. This is the crucial point. This is our key observation about why we can do this, right? And the second thing is that what can we do? The second operation is that we can replace any row, say Ri, with a row multiplied by a scalar lambda. Say lambda is a real arbitrary value, but nothing, okay? We can replace the row with another row multiplied by lambda. Okay, for instance, we can replace row R1 by 2R1, right? But be careful about one thing, that we replace it by multiplying the same row. You see, 2R1. We put 2R1 instead of R1. So this is also a legal operation that does not change the solution set. And another thing is that we can replace the row Ri by Ri plus alpha Rj. In other words, we can multiply another row by a real value named alpha, say it alpha, and then add it to itself and replace the right hand side result by the original row. So this does not change the solution set at all. We proved that in our previous lectures, right? We know these are really helping us to obtain an equivalent system for the original system. Okay, this is, as I said, just a quick reminder before getting to the details of applying Gauss-Jordan method to find the solution. Alright, let's get back to our point. Now we know what a reduced row echelon matrix form is, and what does it mean for us to apply Gauss-Jordan method, and we know what are the legal operations that we are allowed to perform to convert our matrix form into that of an equivalent form called reduced row echelon form. Okay, now let's start. Suppose this is the question. This is our input, right? Suppose this is given. 2a plus 2b plus 4c is equal to minus 2, and minus 4a plus 2b plus c is equal to 4, and minus 6a minus b minus c is equal to 5. Okay, and the question is that apply Gauss-Jordan method to find the solution. Alright then, now we are ready to apply Gauss-Jordan method to find the solution. How do we need to start? Well, our start point is that we need to first convert this system into a matrix form known as augmented matrix, right? This is the first step we need to take before even beginning to apply Gauss-Jordan method or any other elimination method, right? Like Gaussian elimination method we learned in the previous lecture. So how do we do that? We don't forget to put this dashed or dotted line just to indicate that the values to the right of this line are the right hand side values of the equations, whereas the values to the left of this line are the coefficients of the unknown variables. So, and just write them here. Okay, the coefficients in the first equation is that what? We have 2 for the A, we have 2 for the B, and 4 for the C. Okay, let's write them down here. 2, 2, 4, and the right hand side value of the first equation is -2. Okay, how about the second equation? I just write its coefficients, right? -4, and 2 is the coefficient of the unknown variable b in the second equation, and 1 for the c, and right hand side value is 4, right? And for the last equation, we put the coefficients here, the coefficients of the unknown variables, and don't forget the minus sign again. You know, the coefficient of the unknown variable a in the third equation is -6, so be careful about that. And for the b it's -1, and for the c again it's -1, right? So if we use wrong values, then our solution set of course wouldn't be true, right? So be careful about that. And 5 is the right hand side value of the last equation. Now we have the augmented form, right? We put the coefficients along with the right hand side values in the same matrix form, and we formed what is known as augmented matrix form, right? That's the first step. So what is the first step? To apply Gauss-Jordan method. It is also same with the using Gaussian elimination method, right? Augmented matrix form. We need to first represent our system of linear equation in the matrix form to be able to simply apply these 3 elementary row operations. Alright then, let's continue. Now we have the augmented form. And what is the second step of the Gauss-Jordan method? The first step is that you represent your system in the matrix form, which we have just done. And the second thing is we need to check to see if it is in RREF form or not. If yes, then there is no problem, but as we all see, unfortunately it is not in reduced row echelon form, right? Because it is not even row echelon form at all. You see, there is no strictly increasing ladder of zeros here, so there is no zero at all. So the first thing is we need to convert this matrix into what is known as reduced row echelon form, and let's start that. And what it says is that first of all, each leading entry, right? Let's get back to the definition of the reduced echelon form. All right. Well, we know that we must have a row echelon form in the end, but more precisely, the leading entry in each non-zero row must be 1. We should first guarantee this, right? The leading entries, in other words, the very first element, which is not 0 in each non-zero row, should be equal to 1. We need to ensure that. And then in that column, in the leading ones column, everything besides that should be equal to 0. Okay, let's jump into that way and try to convert our matrix. All right, the first step. So this is the very first element in the first row. So first of all, I should start by making this value 1, right? I need to convert this value into 1. The leading entry in the first row should be 1. So how can I do that? First of all, we know that we're allowed to perform 3 elementary operations, and if I replace row number 1 by simply multiplying itself by 1/2 and replacing the row number 1 by the right hand side, then I obtain what I desire, right? So dividing by 1/2, I got what? Let's write it down. 1. Well, I divide both coefficients here by 1/2. In other words, I multiply them 1/2, right? So I got 1 here, I got 1 here, 2 here, and -1 here. Okay. I prefer keeping this line, not to forget that these equations represent both coefficients and right hand side values, and it is a convenient way, by the way. Okay, and there is no change with the other rows for the time being, but of course we will play with them around. Okay, we'll play around with them soon. Okay, let's just write them as they are. -1, -1, 5. Okay, I took the very first step by turning the leading entry in the first row into value 1. It was 2 in the beginning, but now it is 1. Okay, now let's jump into the other steps. So what should I do? The third property says that every other value besides the leading entry in its column must be equal to 0. So I must eliminate these values. -4 and -6 must be 0, right? Because the leading entry in the first row has its column values -4 and -6, but they must be equal to 0. And now my second step, the following step, should be to convert these values into zeros. In other words, what we need to eliminate these values, right? Eliminate, by saying eliminating, I mean converting these values into zeros, so that the coefficient of that unknown variables would be 0, right? They could be eliminated in that equation. All right, let's do that. How can I do that? And while doing that, another maybe key observation that we can make, I don't want to lose the values that I gained so far in this elimination process, right? I can use R1, or I can multiply the first row by some real value and then add it to R2 or R3, so that I can eliminate -4 and -6. Okay, how can I do that? So in other words, I need to write something else, or I need to replace R2 by something else, as well as I need to replace row number 3 by something else on the right hand side, which enables us to have the leading entries equal to 0 in both the second and third row. So I should eliminate this -4 and -6. Their values should be 0. Okay, how can I do that? Well, and of course, for doing that, I need to use R1. Okay, so in other words, I perform the third elementary row operation, right? Okay, let's see. I replace R2, and the single arrow, as we all remember, the single arrow means replace the left hand side row by its equivalent form that I write on the right hand side. Okay, so R2 plus what? If I multiply the first row by 4 and then add it to R2, then, which means 4 times 1 is 4, and if I add this 4R1 to R2, then 4 minus 4 is equal to 0. Then therefore I get a 0 in the very first element of the second row. And the same strategy, how can I eliminate -6? It is simple. I just multiply the first row by 6 and then add it to the third row, and then replace the third row by this equation, right? All right. Now move the cursor a little bit downwards and continue with our computation. Alright guys, then what I got here, let's see. What is the new look? What is the new outlooking of our matrix? Okay. Is there any change in the first row? No. First row remains as it is. So I just put it here, the values of the first row. What has changed in the meantime with these modifications, with these elementary operations, is that the second and the third row, right? Alright, and the second row becomes what? Becomes, here, let's write it down, 0, 6. Of course, be careful about our numerical computations because we add both values in the rows, right? So make sure you multiply all of the values and you add all of them correctly. And for the third row, we got, after this change, 0, 5, 11 and -1, and this is what I get, right, after this modification. Alright then, let's now check to see. Well, and in each iteration, in other words, after each computational step, I check to see if it is in reduced row echelon form or not. If I take a closer look, I'm done with the first column. You see, the leading entry in the first row is 1, and in its column, all the other entries are equal to zeros, right? Okay, now what I'm gonna do? And one thing that we should be careful about is that now I look at the leading entry in the second row. Okay, I'm done with the first row because the leading entry in the first row, in other words, the first non-zero element in the first row is now a 1. So I'm done with the first row in terms of the leading entry. And now I pass to the second row and I see that the leading entry in the second row, in other words, the very first element which is not equal to 0 is 6. But this is not good for us. What we need to do? We need to convert this value into 1, right? Because the leading entry in the second row again must be 1. So how can I do that? It is simple. By performing the second elementary row operation, I replace row number 2, in other words second row, by what? By multiplying the row itself 1/6, right? And this change, after making this change, the new matrix would be, there is no change in the first row, but the second row becomes 0, 1 as desired, 3/2, right, 1.5 in our verse, and 0, right, and the third row remains as it is. We have not done anything to it yet, but we will. And -1. And for the readability, yeah, I put this dashed or dot line again. Alright then, let's continue. Let's continue to our fun. Alright, now let's check to see. Okay, we're done with this part. And we are good to have 1 here because now the leading entry in the second row is 1 as desired. We obtained that, but what can we do now? So the problem is that now in the column of this leading entry for the second row, all the other variables, just like 1 and 5, right? Because let's use another color. You see the leading entry in the second row, which is 1, includes these column variables, and 1 and 5 in the first row there is 1, and in the third row there is 5, right? They are in the same column with the leading entry of the second row. So what we need to do is we need to eliminate the value 1 and 5. In other words, we need to turn them into zeros, and we should do that without losing the information that we have found so far. So I need to use row number 2. By adding row number 2 to other rows, we need to change the first row, the values of the first row and third row. And how can I do that? Let's get back to that. So what I need, okay, now I need to change row number 1 and row number 3 to eliminate the non-zero elements which are in the same column of the leading entry of the second row. So instead of R1, what should I do? R1 plus what? I added itself to row 2 multiplied by some real value. So what is that real value? Of course, you see there is 1 and there is 1. So if I subtract these two rows, then I'm done, because this 1 would be equal to 0. So what I'm doing is I multiply the second row by -1 and add it to the first row. And the same strategy again for the R3, the third row. I add R3 to -5 times R2, because you see, to make this value 0 by using row number 2, what I need to do is just multiply the values in row 2 by -5 and then add it to the row 3. So I got 0 in this value. So our new matrix becomes, let's see what it becomes. Okay, let's write it again. Now the first row becomes 1, right? 0, 1, 0, 1/2, and -1. And second row remains unchanged. I just put the values here: 0, 1, 3/2, transfer 1.5, and 0, right? And the third row becomes 0, 0, 7/2, and -1, right? All right. We walk a long way up to this point, and we are getting closer to the result, the solution set. We're almost there. Now, I check to see whether or not now this matrix is in the reduced row echelon form. And you see, we're done with the first column. We're done with the second column as well. And we are done with the first row and second row. How can I understand that? Because in the first row and in the second row, the leading entries are all 1s, and in the columns that involve this leading entry, all the values are 0s besides this leading entries. Now, I look at the third row, okay? So the third row tells me something here. So when I look at the leading entry in the third row, in other words, I read the values from left hand side to the right hand side in the third row, and I notice that the very first element, which is not equal to 0, is 7/2, 3.5 in other words. So this is not legal for Gauss-Jordan method, because I need to make this value 1. And how can I do that? It is simple. By simply performing the second allowed operation, I reach to my goal. And what is that? I can replace row number 3 to gain the value 1 here. What should I do? It is simple. Just multiply that row 2/7 and replace it by the result on the right hand side that I obtained. Okay, so in this case what I got is, right, let's write it down again and move it a little to the right hand side. Okay, let's keep doing our computation. Okay, the first row is as it is. All right, because we're done with the first row for the time being, and we're done with the second row for the time being, and right there values we have up to this point. But what has changed in the meanwhile is the values in the third row. Okay, 0, 0, and what it becomes is now this is 1, and it's the good news, and this is what? This is minus 2 over 7, right? I do the arithmetic operations, that's what I do. Alright guys, we're almost there. Right, the leading entry here is 1, the leading entry here is 1, and the leading entry in the third row is 1 as well. But what is left behind is one thing. There's only one thing. I look at the leading entry in the third row. This is 1, right? And look at its column. There are the values 1/2 and 3 over 2, 1/2 and 1.5. So I need to eliminate these values. In other words, I got to change these values into zeros. And how can I do that? By simply adding some multiples of row 3 to both row 2 and row 1 to obtain the desired result. Let's do that. Let's see how can I do that. Alright, so okay. And how can I do that again? Right, I put the equivalent sign here. We're trying to converting our original system into an equivalent one, which is given in the reduced row echelon form, okay? Well, actually in the beginning it wasn't, but we will turn it, okay? We're almost there. We're about to turn it into the reduced row echelon form. There's only two simple arithmetic operations left behind. So what am I gonna do is, now I need to change both row 1 and row 2, okay? I need to replace them by something else on the right hand side, okay? R1 is replaced by R1 plus something, and R2 is replaced by R2 plus something, right? And what are these? As we noticed, guys, we have 3 over 2. So if I multiply the third row by minus 3 over 2 and add it to the second row, right, then I got 0 here. And the same thing for the first row as well. If I multiply the third row by minus 1 over 2 and add it to the first row, then I got 0 here. So what I'm going to do is, instead of R1, right, I multiply R3, the third row, by minus half and add it to the first row. And for the second row, I multiply the third row by minus 3 over 2 and add it to the second row, right? Okay, so then our matrix becomes what? Let's see what it becomes. Okay, so the last change here, then we obtain this 1 0 0, right, minus 6 over 7, alright, and second row is 0 1 0 and 3 over 7 and 0 0 1 and minus 2 over 7. That's what we obtained. Okay, now what are we gonna do? We check to see if it is in the reduced row echelon form. In other words, have we reached to our goal? Let's see. All the leading entries in each non-zero row are now ones. And look at their columns. Look at the columns of these leading entries, right? Besides the leading entries in their columns, all the other values are zeros. And our matrix is also in now reduced, is now in row echelon form, right? Because we have no 0 in the first row, but we have one leading 0 in the second row and 2 zeros in the third row. So we have an strictly increasing number of zeros when we move from the top row to the bottom row as desired. So our matrix now satisfies all the three conditions. It is in row echelon form, and each non-zero row has its leading entry 1, and in the column of each leading entry, non-zero leading entry, we have the value zeros besides that non-zero element. So now we obtained what we look for. Now our matrix is in reduced row echelon form as desired, and we are almost done with the Gauss-Jordan method. We applied the technique of Gauss-Jordan method because we started with, okay, let's go back again. We started with what? Alright, this is the original system given to us in the beginning, right? We represent our system in the augmented matrix form and then start to apply 3 elementary row operations that we're allowed to perform on this augmented matrix, and then reach to a point where we can see that we have a reduced row echelon form in the end. In other words, all 3 conditions are satisfied for a matrix to be in the reduced row echelon form. And then what are we gonna do? So we're almost done. As you remember, the only thing left behind is that we apply the back substitution method, and you see that when we apply Gauss-Jordan method, it is even simpler to find the solution set because it avoids us from this computational burden that we have due to applying back substitution method after we reach to this echelon form. So look at that. In the last row, what we have? The coefficient of A is 0, right? 0A plus 0B, right? We substitute back what we found. So we are now converting our matrix back into the equation form, right? And 1C, well, which is just C, right? I don't need to write 1, but just to make things clear, is equal to minus 2 over 7. So there is no computational cost here, almost no computation, because C is equal to, right, you see, minus 2 over 7. That's the advantage of applying Gauss-Jordan method, because if we applied Gaussian elimination method, as you remember, this leading entries shouldn't be equal to 1, right? And also the values in the same column besides the leading entry shouldn't be equal to 0. But when we take into account these values and have a reduced row echelon form, our computational cost is very low, right? Almost there is no computational cost. And in the above equation again, you see 0A plus 1B plus 0C. So we only have B, right? This is the other unknown variable, and B is equal to 3 over 7. It's just as simple as that, right? We don't need to divide the coefficient of unknown variable, both sides. We don't need to even divide both sides by the coefficient of the unknown variable, because the coefficients are equal to 0, right? And for the first equation, 1A plus 0B plus 0C is equal to minus 6 over 7, which means A is equal to minus 6 over 7. And this means we found the solution. In other words, we found the 3 tuple that satisfies all the equations in this given system simultaneously, and our solution is what? Our ABC 3 tuple is nothing but the values that we have just found, right? A is equal to minus 6 over 7. I wrote them in the same order of the unknown variables, in the order of ABC, like this, okay? And 3 over 7 and minus 2 over 7. This is the solution that we have found by applying Gauss-Jordan method to the given system. And in other words, this is our output, guys. This is what our algorithm produces. Alright, so Now we understand, in this lecture we understand and we learned what a reduced row echelon form is, how can we convert a matrix into that of a reduced row echelon form if it is not in that form, and what does it mean for us to apply Gauss-Jordan method, the steps that we need to follow to apply Gauss-Jordan method. And with an example we see that how we can find the solution to a given system by just applying that technique known as Gauss-Jordan method. Okay guys, there is one important thing to note before completing this lecture. Up to this point in this lecture series, we usually, well, not usually, so far we have always reached to the solution set. We have a unique solution, right? So I found a tree tuple because I have three unknown variables here based upon my equation given in the first way, right? Given in the first place here, you see ABCs are unknown variables. So I'm looking for an ABC tree tuple that satisfies this system if it is possible, right? And again, until this point we always have found such a solution, a single solution, which is the case of unique solution, right? But we know based upon our previous lectures that actually we have three possible options for finding the solution of a system. And what are the other two options? You know, up to this point we only have had the unique solution case where we reach to the exact solution, the only solution that satisfies all the equations. But we also have two other options. One is that even we may not have a solution at all, right? So the empty set case. So if there is no solution, it is possible, right? It doesn't mean just because we are given a system and we are looking for the solution of it, that guarantees that we will absolutely find a solution. There may be no solution, right? In other words, there may be no tuple that satisfies all the equations at the same time, the empty set case. Okay, and another option is that the third one is, you know, there can be also infinitely many solutions, meaning that if the system is satisfied an infinite number of tuples, then we have the infinite solution case. Okay, and in our next lecture I will show you how can we reach to these other two possibilities where we have either empty set, or in other words when there is no solution, and when we have an infinite number of solution case. And up to that lecture, have fun guys, and see you in the next lecture.